Look at your water bill. Then look at your electricity bill. A significant portion of both comes from watering your garden and your fields. Every time a pump runs, a meter turns. Every time the irrigation system cycles on, somewhere a wire is carrying current that you will pay for at the end of the month. On Amish farms across Pennsylvania, Ohio, and Indiana, those meters have not turned for irrigation since the early 1800s. 40 acres watered, crops sustained through July and August heat, gardens producing through dry spells that wilt unmanaged plantings within a week. All of it accomplished without a single electrical cable running to a pump, without a single motor running, without a single control valve requiring a battery or a timer or a service technician when it fails. The only force the Amish Hillside water system requires is the one that has been available for free since the first farm was ever carved into a slope: gravity. The modern irrigation industry cannot sell you gravity, so it has spent a century and a half convincing you that gravity alone is insufficient, that you need pressure, that you need pumps, that you need the infrastructure of purchased water delivery. Amish farms have been quietly proving otherwise on the same hillsides, with the same water, using the same physical principles since before that industry existed. The physical principle behind the Amish Hillside water system is one of the oldest and most reliable engineering principles ever applied to agriculture. And its suppression from mainstream farming practice in the 20th century has nothing to do with its effectiveness, and everything to do with who profits when water moves through a pipe. The principle is hydraulic head, the pressure created by the weight of water at elevation above the point of delivery. Water is heavy. A column of water 1 foot tall exerts approximately 0.43 pounds per square inch of pressure at its base. A spring or collection pond positioned 30 feet above a crop field delivers 13 pounds per square inch of water pressure to that field without any mechanical assistance whatsoever. 60 feet of elevation delivers 26 psi. 100 feet delivers 43 psi, the same working pressure as a typical residential water supply. On any farm with meaningful topography, the elevation difference between the highest reliable water source and the lowest field to be irrigated contains enough hydraulic head to drive a complete irrigation system from one end of the property to the other, at usable pressure, without a motor, without electricity, and without any component that requires purchasing after the initial pipe installation. The Amish understood this not as hydraulic engineering, which they had no formal language for, but as observation. Water flows downhill, and if you guide it correctly from a high point to a low point through a closed pipe, it arrives at the low point with enough force to water a field. The modern irrigation industry understood it too, which is precisely why it worked so hard to replace the principle with equipment. Because you cannot sell a farmer his own hillside. The construction of the Amish Hillside water system began with the most important decision in the entire project: the selection and development of the water source. On most Amish farms in the Appalachian and Midwestern regions, the primary water source was a hillside spring, a point where groundwater emerged naturally from the slope at a consistent flow rate year-round. Springs in these geological formations are fed by aquifers that recharge through seasonal precipitation and are often remarkably consistent across years and decades, providing a reliable flow even through dry summers when surface water sources fail entirely. The Amish developed their springs with a specific construction sequence that maximized water collection, protected the source from surface contamination, and created a reservoir with sufficient volume to buffer the irrigation system through periods of peak demand. The spring was first cleared of surface vegetation within a radius of several feet. Then a collection chamber was excavated, a stone-lined box, typically 2 to 3 feet deep, and wide enough to allow sediment to settle before water entered the outflow pipe. The chamber walls were dry-laid fieldstone on 3 sides, allowing groundwater to seep in from the hillside while keeping surface water out. The 4th side, facing downhill, was a mortared stone wall with a single outlet pipe positioned near the top of the chamber, ensuring that only the clearest settled water entered the distribution system. The collection chamber was then covered with heavy flat stones or timber, preventing surface contamination and evaporation losses. This simple construction, fieldstone, clay mortar, and a single outlet pipe, created a self-cleaning, gravity-fed water source that required almost no maintenance, and that many Amish farms have relied on for over a century without modification. The pipe network that carried water from the spring collection chamber to the fields below was the engineering heart of the Amish Hillside system, and the material choices that governed its construction determined whether the system lasted 5 years or 100. The Amish used 2 primary pipe materials depending on availability and terrain. The first was fired clay tile, sections of dense, fired ceramic pipe typically 4 to 6 inches in diameter, that were produced locally in the same kilns used for building brick and roofing tile. Clay tile is chemically inert, biologically resistant, and mechanically stable over long time periods when properly laid in undisturbed soil. A correctly laid clay tile line on a stable hillside slope does not corrode, does not degrade from chemical interaction with soil or water, and does not fail from pressure cycling. Multiple Amish clay tile irrigation lines from the 1850s and 1860s have been excavated in good condition during farm improvements more than a century after their installation. The second material was board log pipe, sections of straight-grained hardwood log, with the center bored out using a long auger, fitted end-to-end and sealed at the joints with pine pitch or tallow-rendered hemp. Board log pipe was less durable than clay tile in wet soils, but significantly easier to produce in areas where clay kilns were not available, and it provided excellent service life in well-drained hillside soils, where the wood remained consistently dry between irrigation periods. Both pipe types were laid in shallow trenches following the natural contour of the hillside, with a consistent downhill grade maintained throughout the run to prevent airlocks and ensure steady gravity flow. The grade calculation was simple: enough slope to move water at the required flow rate, not so much slope that the velocity eroded the pipe joints at connection points. The Amish farmer who laid his own pipeline calculated this grade by eye and by water, laying a section, introducing water, and watching how it moved before deciding whether the next section needed more or less slope. The distribution system at the field level, the way the Amish moved water from the main gravity pipe to individual crop rows, was the element of the system most precisely calibrated to the specific needs of each crop and most carefully managed to avoid the water waste that would deplete a gravity-fed supply faster than the spring could replenish it. The main pipe from the spring terminated at a simple stone distribution box at the upper edge of the crop field, a small stone-lined chamber that received the full gravity flow and divided it into smaller channels running to individual field sections. The distribution box had no mechanical valve, no timer, no electronic controller. It had wooden gate boards, flat planks that could be inserted into slots cut into the stone channel walls to open or close individual field section flows by hand. The farmer walked to the distribution box each morning of an irrigation period, assessed the moisture condition of each field section by feeling the soil, and adjusted the gate boards to direct water where it was most needed. Overwatered sections received a closed board. Dry sections received an open channel. The system required judgment, not technology. It rewarded the farmer who knew his land, who understood which sections drained fastest, which retained moisture longest, which crops were approaching stress before the leaves showed it. This knowledge, accumulated across seasons of observation, made the distribution management more precise than any automated timer system because it responded to actual soil condition rather than to a program schedule that could not know whether last week's rain had saturated one section while leaving another dry. The gate boards cost nothing. The stone distribution box was built once. The knowledge of how to read the soil and adjust the boards was passed from father to son across every generation of Amish farming that worked the same hillside. The maintenance demands of the Amish Hillside water system across a full season and across decades of operation were minimal, to the point that a modern irrigation contractor would find them implausible. The spring collection chamber required clearing of leaf debris from around the coverstones each spring before the irrigation season began, a task of perhaps 30 minutes once a year. The chamber interior was inspected annually for sediment accumulation at the floor, which was removed by briefly diverting the spring flow while the chamber was cleaned with a long-handled scoop. This annual cleaning required perhaps 2 hours and prevented sediment from reaching the pipe system. The pipelines themselves, correctly laid in stable hillside soil, required almost no maintenance. Clay tile pipe in undisturbed soil does not corrode, does not accumulate biological growth at a rate that impedes flow, and does not fail from internal pressure variation because the gravity pressure it carries is modest and consistent. A pipeline that was correctly graded at installation continues to flow correctly across decades without adjustment. The distribution box and gate boards required the most frequent attention. The wooden boards warped slightly with seasonal moisture changes and needed replacement every 10 to 20 years, a task requiring a saw, a few planks of local lumber, and an afternoon. The stone box itself required no maintenance beyond occasional repointing of mortar joints, a task performed at the same interval as other farm masonry maintenance. Comparing this maintenance profile to a modern electric pump irrigation system, with its annual pump servicing, filter replacement, valve testing, electrical connection inspection, pressure gauge calibration, and the periodic complete pump replacement when the motor fails, the Amish system's maintenance demands are not simply lower. They are a different category of requirement entirely. One system degrades continuously and requires continuous investment to maintain its performance. The other operates at designed performance indefinitely, requiring only the removal of what accumulates naturally and the replacement of the one wooden component that weathers over time. The Amish Hillside water system did not disappear from American farming practice because irrigation technology improved past it. It disappeared because the expansion of rural electrification in the 1930s and 1940s made electric pump irrigation the path of least resistance for any farmer connected to the new electrical grid, and because the agricultural equipment industry that grew around that infrastructure had every commercial incentive to promote pump-based irrigation over gravity-based systems that required no ongoing equipment purchase. The Rural Electrification Act of 1936 brought electricity to American farms at subsidized rates, specifically designed to make electrical farm equipment economically attractive compared to non-electrical alternatives. A gravity irrigation system that had been working without operating cost for 60 years suddenly had a competitor that was cheaper to install, easier to explain to a county extension agent, and actively promoted by equipment dealers who profited from pump sales, motor replacements, and service contracts. The knowledge of gravity system design and construction did not disappear overnight. It faded across a single generation. The farmers who had grown up using gravity systems died, and their children, connected to the grid and surrounded by pump equipment promotion, did not learn what their fathers had known. By 1960, the gravity-fed Hillside water system was listed in American agricultural engineering texts as a historical method, appropriate only for areas without electrical access. By 1980, it was not listed at all. On Amish farms, where the electrical grid connection was never made, and where each generation learned water system management from the previous one through continuous practice, the knowledge survived intact. The springs that fed those systems are still flowing. The clay tile lines that carry the water are still intact. The stone distribution boxes are still managing the morning flow. And the farms they irrigate are still producing crops in dry summers, when their electrified neighbors are watching pump electricity bills climb and wondering whether there was ever a different way to move water from a hill to a field. There was. There still is. And it has never required anything that a farm hillside does not already provide. Leave a comment below. Does your property have a slope and a water source at a higher elevation than your garden? Tell me your terrain. If this breakdown gave you a clearer picture of what a self-sufficient water system actually looks like when it is designed around physics rather than around purchased equipment, subscribe. There is more thinking like this where it came from.